Hello kids and welcome to titrations. So today we're going to learn how to conduct a titration, and we're also going to learn how to use our data from building a titration, from participating in a titration to find either the volume of one of the substances or the concentration of one of the substances. And guess what, kiddos? Guess what's back? Stoichiometry. You thought it was over. It's not. It's back. So let's take a look at some titrations, shall we? Let's take a look at the experimental design for analysis. Experimental designs discussed so far have been qualitative. Flame test, solution color, litmus test, conductivity, solubility. These are all qualitative. Now, with titrations, we use qualitative analysis and quantitative. So quantitative experimental designs allow measures measured amounts to be obtained. The experimental design chosen for analysis depends on what equipment we have, right, and our time. So moving on, there are 4 types of analytical experimental designs, right? There's crystallization, filtration, gas collection, and finally what we're going to learn today is titration. So in a nutshell, you have a solution in a burette. We call this solution inside the burette a titrant, and that is progressively added to a measured amount of volume of another solution. We call this solution a sample. We put the sample in a specific piece of glassware, which is called an Erlenmeyer flask. That is a non-negotiable, kiddos. The volume of the titrant at the endpoint is measured. So let's take a look and see what is exactly going on. If you see this diagram, it basically shows up how to set up a titration, okay, kiddos? Here's your Erlenmeyer flask. It's specifically your Erlenmeyer flask. You have your sample in your flask. In your sample, you also put a few drops of indicator. You have to use your qualitative analysis, so you have to take a look at color change in this particular example with titrations in order to figure out what is going on, when to stop this titration. Here we have something called the burette. A burette is a very long piece of glassware, and it's graduated, which means that there's little ticks along the side of the burette. So let's go over this, shall we? It's a common experimental design used to determine the amount of concentration of substances in solution. The solution of a known concentration may be either the titrant or the sample. It makes no difference to the analysis. So you have to know the concentration of at least one of the two, okay? So if you're looking for, because it all depends on what you're looking for, right? But you have to have the concentration of at least one. That's a given. It's either the concentration of the solution in the sample or the concentration of the solution in your burette. So the solution of the known concentration may be either one. Carefully adding a solution, you're adding your titrant from your burette into a measured fixed volume of another solution, the sample, in an Erlenmeyer flask until the reaction is judged to be complete. So your sample is always the same in terms of volume. So if you have a sample of 10 mils, what you have to do is that every single sample has to be exactly 10 milliliters, okay? And you use a pipette to measure those exact 10 milliliters, if that's the exact. It could be 15 milliliters. It all depends on what how large your sample is, but that doesn't change. The sample does not change. The burette is a precisely marked glass cylinder with a stopcock at one end, and that's this little guy. It's kind of like a valve that allows you to add the substance into your Erlenmeyer flask a little bit at a time. Allows precise, accurate measurement and control of the volume of the reacting solution. When doing a titration, there will be a point at which the reaction is complete, when chemically equivalent amounts of reactants have combined. This is called the equivalence point. Okay, I'm going to go a little further and compare really quickly, go through these notes really quick, and then compare the equivalence to the equivalence point to the end point. So here you have your equivalence point, and here you have your end point, okay? Because they're the same, it happens at the same time, but you're looking at the titration from a completely different perspective, okay? So let's go back into the definition of an equivalence point. It's when chemically equivalent amounts of reactants have combined. This is very important because when we're talking about chemically equivalent amounts, we're talking about number of moles. So you have the same number of moles of your reactants so in this case the sample and the titrant, equivalent amount of moles of those two when they have reacted with each other. Once that happens, it's called the equivalence point. But obviously, we can't see that. Like we can, in theory, understand that it's the exact same amount of moles reacting. They've reacted, but there's no way we can be like, oh, it happened now, because we can't see that happening. That's why we use the endpoint to tell us, okay, I need to stop the titration. I think I'm good. So to recap, equivalence point, the point during a titration at which the exact theoretical chemical amount, here we have another special word, chemical amount, you know, that means number of moles, of titrant has been added to the sample. Okay, to measure this equivalence point experimentally, we look for a sudden change in an observable property such as color, pH, or conductivity. This is called the endpoint. So we use our endpoint with titrations is when you have a permanent color change to tell us, oh, we've reached the equivalence point. But the equivalence point and the endpoint are at the exact same time. The equivalence point is the theory behind the color change, if that makes any sense. Okay, so an initial reading of the burette is made before any titrant is added to the sample. So you always have to measure your initial reading. Makes sense. Then the titrant is added until the reaction is complete. How do we know the reaction is complete? It's when you have when a final drop of titrant permanently changes the color of the sample. So here's our sample, for example. Let's say we add an indicator there and it's yellow, right? We have this sample, and every other subsequent sample is going to have the same amount of volume. So let's just say, for example, 10 mils. We add to it some indicator, and we know that at some point that indicator is going to change color. And sometimes it's really kind of magical when you add your titrant to the sample. Notice here how there's like a little color change. If I swirl the aroma flask, that will disappear. The color will disappear because it's reacting. The moles, the reactants are reacting, like the titrant and the sample, they're reacting. At some point, one little drop is going to go in here and it's going to change the color permanently. I can swirl it and it won't change color anymore. At that point, you are done and your titration is over, and we take the final burette reading. And once that happens, the final burette reading is taken. The difference between the readings is the volume of the titrant added. So then I subtract my initial burette reading from my final burette reading, and I get an amount of volume. That volume is the volume from your titrant that was used to react fully with my solution, which is my sample. I know, right? A titration should involve several trials to improve the reliability of the answer. A typical requirement, this is really important, kiddos, a typical requirement is to repeat titrations until 3 trials result in volumes within a range of 0.2. If you do a trial, if you complete a trial and the difference is more than 0.2, you actually have to do it again, because ultimately you want 3 values that are all within 0.2. These 3 results are then averaged before carrying out the solution stoichiometry calculation. Disregard any trial volumes that do not fall in this range. Okay? Here's some tips. Any property of a solution such as color, conductivity, or pH that changes abruptly can be used as an endpoint. However, some changes may not be very sharp or may be difficult to measure accurately. This may introduce error into the experiment. Any difference between the titrant volumes at the empirical or observed endpoint and the theoretical equivalence point is known as a titration error. Okay, how to read a burette? What you have to do is you have to take a look at the meniscus. Do you guys remember the meniscus? It's like when any kind of water, so a solution obviously has water in it, when it goes in, and you can't see it very much in a beaker, but definitely in a very slender piece of glassware, you can see that the water curves. You have to measure to the bottom of the meniscus, okay? So readings will always be lower than 1. All that means is that don't fill up your burette higher than 0. Okay, obviously that makes sense. Okay, alrighty. So now Let's take a look at a sample problem. Determine the concentration of the hydrochloric acid in a commercial solution. So this is what we're doing. We are tasked with finding the concentration of the hydrochloric acid. Okay, so let's take a look at all the data that we have. A 1.59 gram mass of sodium carbonate, and there's the chemical formula, Na2CO3 solid, was dissolved to make 100 milliliters solution. Samples that are each 10 mils of this standard solution were then taken and titrated with the hydrochloric acid solution. The titration evidence collected is below. Methyl orange indicator was used. Okay, so let's take a look at all the information that we have. We have 1.59 grams of sodium carbonate, and it's dissolved in 100 milliliters of solution. We know that C is equal to N over V, so concentration equals number of moles over volume. Volume with this formula always has to be in liters. So first thing I'm going to do, and I'll go over this, it's in the next slide. We have to convert milliliters to liters, and then guess what we have to do here? We have to convert your grams to moles, and then divide your moles over your volume to get your concentration, right? Because that will give us the concentration of the sodium carbonate. We also know that the samples, each of the samples are 10 mils. What we have to figure out with this table is the volume of the titrant. Okay, so how do we do that? What we have to do is take a look at our final burette readings and your initial burette readings, subtract them, and we get these 4 readings. Okay, let's take a closer look at the 4 readings. So this is your quantitative data, and this is your qualitative data. So let's take a look at these readings, 12.8, 12.8, 12.7. These 3 are all within 0.2. This guy is way higher. It's 13.1. He's your outlier. We don't use it. Okay. Take a look at the colors at the qualitative data. Orange, 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 red. Obviously, they added too much titrant because it went from permanent, 1 drop being a permanent color change to way too much to actually make it go red. Okay, so what do you do with these 3 kiddos, the 12.8, 12.8, and 12.7? We average them out. Do you guys remember how to average? 3 things, add the 3 things together, divide by 3. If there were 4, you would add the 4, divide them by 4. Make sense? Okay, in titration analysis, the first trial is typically done very quickly. It is just for practice to learn what the endpoint looks like and to learn the approximate volume of titrant needed to get to the endpoint. Greater care is taken with subsequent trials. Okay, first, you're going to determine the concentration of the 100 milliliter solution of carbonate of the sodium carbonate solution. So I have my 1.59 grams. I'm going to use my molar mass to get to moles, and I'm going to divide it by 0.1 because it has to be changed to liters. And we get our concentration of 0.150 moles per liter. The second step, write a balanced chemical equation. So there's our balanced chemical equation, and we are populating it. Okay. So here's our sample. And there's the volume of our sample. There's the concentration of our sample. We've identified that we're looking for the concentration of the hydrochloric acid, and we have the 12.8, and it's a rounded value. Okay, kiddos, it was rounded, and that's the averaged volume. Okay, so what we're going to do now is we're going to use our friend stoichiometry to compare these two, right? Because we're comparing the hydrochloric acid with the sodium carbonate. And we see that it's a 2-to-1 ratio. So we always start with everything with the place, the substance, the entity, where it gives us a lot of information, and this is it. We are going to start off with the amount of volume because then I can use that to cancel out my liters. Now, here's very, very important. Notice that there's 2 volumes here. And notice they're both in milliliters. If that's the case, leave them if you want. You don't have to convert them to liters in this situation here because they'll kind of cancel each other out anyways. Notice how here is my milliliters and here's my milliliters. They're going to cancel anyways. Not a big deal. So then I use my solution to cancel out my volume, and then I have my moles, and then I use my molar ratio, right? This is what I have. So this is moles of sodium carbonate, right? And this is for what I need to find. And obviously I'm looking for HCl. And then I have to just make sure, this is a really important step, that it's 1 over my volume, right? Because I want to keep the volume, and that's going to get me my concentration of 0.234 moles per liter. So we're taking, that's not new, kiddos. You've already learned solution stoichs, so that's not new at all. So let's summarize. Titration is the technique of carefully controlling the addition of a volume of solution, the titrant, from a burette into a measured fixed volume of a sample solution until the reaction is complete. The concentration of one reactant must be accurately known, obviously, because we want to usually find something else. The equivalence point is the point at which the exact theoretical stoichiometric reacting amount of titrant has been added to the sample. So the equivalence point, remember, we're looking at the number of moles of the reactant and number of moles of the second reactant, so the titrant in the sample, have been used up to react with each other, right? The equivalent number of moles. The endpoint is the qualitative data that we get to tell us that we've reached the equivalence point. The endpoint is the point during the titration at which the sudden change of an observable property indicates that a reaction is complete. Several trials must be completed. When at least 3 trials result in values that are within a 0.2 millimeter range, those values are then averaged, and we typically like 3, but sometimes you get 2. The average value is used for the stoichiometry calculation. Okay, that's it, kiddos. So just so you know, I'm going to be adding on some fun stuff for you to do. So keep posted and have a great day.